Now let's talk about how you can calculate the wavelength of light that gets absorbed by a complex. We're told that the d orbital splitting in an octahedral transition metal complex is 160 kilojoules per mole, and we're asked to find the wavelength of light absorbed. The reason why I'm going through this example is because it's so important to really watch out for the units here. This is an area where students commonly make mistakes, which is why I wanted to do this as an example here. So the way that we're going to solve this problem is by recognizing that the crystal field splitting, right, that's our delta E, that's going to be equal to the energy of the photon. And we can relate the energy of the photon to the wavelength of light absorbed from the equation E photon equals hc over lambda. Now my goal is to find wavelength, so I'm going to cross multiply through this equation to solve for lambda, giving me that lambda is equal to hc over E of the photon. So all I did was multiply both sides by lambda and then divide both sides by E photon. Next, I'm going to begin plugging in numbers. So the wavelength of the light that's going to be absorbed will be equal to h, which is Planck's constant, and that carries a value of 6.626 times 10 to the minus 34, and the units are joules times seconds. That's a constant, and that is on your information page. C is the speed of light, which is also given on the information page, and carries a value of 3 times 10 to the 8th meters per second. We divide that by the energy of the photon, which is identical to what the crystal field splitting is, 160 kilojoules per mole. And now we're going to take a look at the units here. It's so important to always write out all of the units because in doing that, you can check to see whether or not you have to do more conversions to get to the answer. At this point, we recognize that yes, seconds do cancel out, so that's nice. But on the top, we have energy in units of joules, and on the bottom, we have energy in units of kilojoules per mole. So we have some work to do to make units compatible here. Firstly, I can convert the kilojoules into joules by multiplying by 1,000 here. So 1,000 joules in a kilojoule. And now I've converted the kilojoules into joules. So kilojoules cancel, and then joules cancels the joules that are on the top from the units of H. However, we still have units of moles left over. And so that's a problem for us, right? There's no such thing as wavelength in units of meters moles. We've got to get rid of the moles. And to think about how we will do this, it's important to recognize that the crystal field splitting that you're given tells you how much energy gets absorbed per mole of the complex that you're dealing with. When you're using the equation E photon, that's dealing with single photons, single molecules, single electrons. So we have to convert from having a mole of the substance to having individual photons. And what conversion factor connects you from having a mole of something to having individual particles? It's going to be Avogadro's number. So that's what we need to introduce now to cancel out the moles. Avogadro's number tells me that 1 mole contains 6.02 times 10 to the 23 items. So I want to put the 1 mole on the top so that the units of moles cancel out, and then that means 6.02 times 10 to the 23 goes on the bottom. Again, writing out the units helps you to recognize that this step needs to be done. It also helps you to know where to put the 6.02 times 10 to the 23, right? It's telling you to divide by Avogadro's number. If you don't write out the units, you might end up accidentally multiplying by Avogadro's number, and then you're going to end up with an answer that is off by 46 orders of magnitude, which is like a lot. The moles cancel out, and now all that's left is units of meters. And that's a good thing because we're calculating a wavelength, and so that's all the units should be. So everything works out here. You'll plug this into your calculator and definitely get practice with this so that you know how many parentheses you need in order to get all the numbers to multiply out correctly. The number that you'll get will be 7.48 times 10 to the minus 7 meters. And it's often inconvenient for us to express wavelength in units of meters, especially when we're talking about things that are in the visible range of the spectrum. And so we often like to convert to nanometers, which is a bit more convenient. This is another conversion factor that you're given, which says that 1 nanometer is 10 to the minus 9 meters. So you would divide by the 10 to the minus 9 meters so that the units of meters cancel out. And now you're in nanometers. And that tells you that the wavelength of light that's absorbed is 748 nanometers. Just For the sake of completeness, I will mention here that if you were to look at the visible spectrum, you would see that a wavelength of 748 nanometers is a red color. So red light is going to be absorbed, meaning that you would observe the complementary color, which is green. So you would observe green. And you're able to determine all of this by knowing the crystal field splitting by using the equation E equals hc over lambda to convert the crystal field splitting into a wavelength of absorbed light. Then you can use the color wheel to tell you what color is going to be observed. I will also again caution you about the units here, right? We have that the units of H contain joules. That's joules per individual photon. And the crystal field splitting is given to you in kilojoules per mole of complex ion. So to go from having a mole of the complex to having single photons, you need to divide by Avogadro's number. All right, that brings us to the end of this video. And next, what we're going to do is talk about magnetism, another important property of transition metal complexes.